Good morning, class. So today we're going to be talking about electric fields, and we're going to be talking about those electric fields and how we can use them to understand electrical energy and then how circuits work and power, if you'll pardon the pun, the entire world around us. So before we get started with electric fields, let's revisit gravitational fields for a moment. So what causes objects to fall? And the short answer to that, of course, is gravity. But what is gravity? And that is a much, much harder question. So much harder that if you were to answer that, that would get you a Nobel Prize. Because we really don't understand how gravity works on the quantum level. However, what we do know is that however that works is going to involve gravitational fields. So Earth has a gravitational field. We know this because we can watch objects fall, and also we have done problems with that in the past because we know that the strength of Earth's gravitational field is given by 9.8 newtons per kilogram. One thing that we can also do is draw gravitational fields. So the arrows for the gravitational field show the direction of force for an object with positive mass. And I put positive there in parentheses because all mass is positive, but when we get into charge, it's going to be a little bit different. Now, all mass is positive. If you prove me wrong, you get another Nobel Prize. So, a couple things here. The denser the lines, the stronger the gravitational field. So looking at the pictures of the round Earth, as you go out, those lines get further and further apart. And that means that the gravity gets weaker. So if you go about 250 miles up, that's where the International Space Station is, and there Earth's gravity is only about 95% as strong as it is here on the surface of Earth. The astronauts are weightless only because they're in free fall. They still have 95% of their force of gravity, so weightless isn't quite right. Normal forcelessness is the better term, but that just doesn't trip off the tongue. So going further out, if you go 250,000 miles out, you get to the moon, and there at the moon, which is way far away, the Earth's gravitational field is only about 0.2% as strong as it is right here standing on the planet. And of course, objects that have bigger mass have bigger gravitational fields. Jupiter has 860 times the mass of Earth, so it has a much, much stronger, 860-ish, times stronger gravitational field. And the sun is much, much bigger. And as you get into larger and larger objects, like the supermassive black hole at the center of our galaxy, it becomes ginormous. Technical. So now let's talk about electrical fields. So everything that has charge produces an electrical field around it. Field interactions is what causes the attraction and repulsion that you learned about in previous science classes. So, electric fields can be drawn just like gravitational fields. And the arrows show the direction of force for an object with a positive charge. So, since opposites attract, that means that the field lines would need to go in to a negatively charged object, because this is showing the direction of force on a positive charge. Similarly, because like charges repel, the field lines are going to go out of a positive charge, because that's going to be forcing another positive charge away. And these field lines can interact and add together and cause that repulsion and attraction and do all sorts of interesting things. But what we're going to be concerned about is that you can make a uniform electric field, and that just means a constant electric field, one that's not changing, by having two charged plates. So if you have two charged plates, then in between those plates, you're going to have a constant, unchanging electric field that you can then use to do easy mathematics. So, just like what we saw in gravitational fields, when you have a point charge, the further away you get, that electric field is going to drop off dramatically. And objects that have bigger charges have bigger electric fields. So let's see. Oh, and the strength of the electric field is given in newtons per coulomb. That's units of force over units of charge. And coulombs is going to be the unit of charge that we're going to be using throughout the rest of the year. So let's see how we can go about calculating forces. So we're going to do gravitational forces and electric forces as seeing how those work together and how they're similar and how they're different. So gravitational forces depend on the strength of the gravitational field, given as G, and the object's mass, M. So this is the equation that we've been using for the last couple months. The force of gravity is equal to the mass of an object times the strength of the gravitational field. In an electric force, the strength of the electric field and the object's charge, again given in coulombs, it gives you the strength of the electric force. So, written out, this would be the strength of the electric force is equal to the strength of the electric field times that charge in coulombs. So, let's do an example. So, gravitational force. Find the force of an object that's 100 kilograms in Earth's gravitational field. All right, we can do that. So that's going to be the force of gravity equals that mass times the strength of the gravitational field. We know what the strength is because we're on Earth. That's a constant. So that force of gravity is going to be 100 kilograms times that constant, 9.8 newtons per kilogram. Do a little math and we end up with that force of gravity for this object being 980 newtons. So let's try dealing with an electric force now. Find the force on a 100, there's that backwards U thing again. And that backwards U, you might remember, is the Greek letter mu. And in this context, it means micro. Micro is 1/1,000,000th, or one more delineation past milli. So it is going to be 1/1,000,000th, or 1 times 10 to the minus 6 coulombs. This is going to be a kind of metric prefix that we're going to be using a lot in this unit because 1 coulomb is a truly, truly massive amount of charge. So a lot of times, even a strongly charged object like this one, you're still going to be measuring in microcoulombs. So we have this 100 microcoulomb charged particle in a 20 newton per coulomb electric field. And because the electric fields are all going to be different, that will need to be given or, in some cases, solved for. So that electric force is going to equal the strength of the electric field times the charge. So plugging in some numbers, we have that electric force is going to equal 20 newtons per coulomb times 100 times 10 to the minus 6 coulombs. So those coulombs are going to cancel out, and what we're going to be left with is going to be 2 millinewtons, or 2 times 10 to the minus 3 newtons. So let's talk about energy now. So gravitational energy is dependent on the mass of the object, the strength of the gravitational field, G, and the height that you are, or rather the change in height from where you put your 0 point. And electric energy depends on the strength of the electric field, E, the object's charge, Q, and again, that change in distance in the field. So the equation for this is going to be that electrical energy is equal to that strength of the electric field times the charge times the displacement that you go inside the field. So let's do some math on that one. So same numbers, we've got we're looking for the gravitational potential energy of that 100 kilogram object. Now we've raised it 2 meters up in the air. So gravitational potential energy, that's going to equal the mass times the gravitational strength times h, that's the height that we've moved up in the field. So that's going to be 100 kilograms times 9.8 newtons per kilogram times that distance that we've moved up in our gravitational field. So that works out to be 1,960 joules. We can do something similar when it comes to the electrical energy. So same particle, 100 microcoulombs. Now we're going to be looking at it traveling 10 centimeters up. So that's basically if you've got that electrical field pointing down, or it could be pointing to the left or pointing to the right, then it's going upstream against those arrows in the electrical field. So that electrical energy is going to equal the electrical field times the charge times the distance that you've gone in it. So 20 newtons per coulomb times 100 times 10 to the minus 6 coulombs, that's the 100 microcoulombs, times 0.1 meters, doing that conversion from centimeters to meters, is going to give us 200 times 10 to the minus 6 joules, or 200 microjoules. So, hopefully this isn't anything too new. We're just taking those same concepts that we have used and looking at them in a new way. And we know that this is just looking at it in the new way because if you look again at that electrical energy, we've got the electrical field times a charge. That's the force times the distance. So force times distance, that's work, that's change in energy, and that of course is going to give you that change in electrical energy. What we're going to do now is look at this in a slightly different way, regroup some things. So let's now talk about potential. And this is going to be different than potential energy for reasons that we're going to see shortly. Let's first talk about gravitational potential, and we'll see how then electric potential is going to differ. So, the gravitational potential is the energy per unit mass at a position in the gravitational field. So this depends on the strength of the gravitational field, G, and the height that you've moved in that gravitational field. So this isn't really used all that often in physics unless you're doing things like orbital calculations, moving between one celestial body and another, for instance the Earth and the Moon, or going from the Earth to Mars. But you can still use this to solve problems. And you could use the equation so that gravitational potential is equal to G, that gravitational field strength, times the height that you've moved in it. So let's talk about electric potential. And we're going to see that this is a lot more useful to us. So this is the energy per unit charge, again, that's going to be in coulombs, at a position in an electric field. So this depends on the strength of that electric field, E, and the distance that you've gone in that electrical field. So this is used all the time, especially because just like in gravitational potential and gravitational potential energy, there's no one sign in the universe that says, here there is zero. So we're going to be dealing with this in relative terms. You'll hear potential difference a lot. Another thing is that the electric potential is easy to measure. It is much harder to measure the strength of an electric field. So this becomes a very, very useful measurement, as we'll see as we continue along in the unit. It's so useful that it's given its own name, voltage. And this is something that you've probably encountered a lot in your daily life. So voltage is going to equal that strength of the electric field times the distance that you've moved in it. So let's do some calculations with this and see how it works. So using the same numbers that we have been, calculate the gravitational potential 2 meters above the Earth's surface. So that gravitational potential going to equal that strength of the gravitational field times the height that we've moved in it. So this is going to be 9.8 newtons per kilogram times 2 meters. And this is going to give us a gravitational potential for that point that's 2 meters above the Earth's surface as 19.6 joules per kilogram. So if you wanted to figure out how much potential energy you'd have in joules, you would multiply the mass of anything sitting at this point 2 meters above the Earth by 19.6. Let's see how this works for electrical potential. So calculate the electric potential, the voltage, 10 centimeters up in an electric field of 20 newtons per coulomb. So these are the same numbers that we've been using. So the reason why I said up is because in a gravitational field, down is defined as the direction that the gravitational field lines are going. That's the direction that an object that has a positive mass falls when you drop it. Up means that we're going against those electrical field lines, so we're going to be gaining energy. We're going to be gaining gaining energy if we have a positive charge. So we're going to be gaining that electrical potential as we go up that electrical field. We're going against the electrical field lines. So the voltage is going to equal that electrical field strength times the displacement in our electric field. So 20 newtons per coulomb, we're going 0.1 meters, that's that 10 centimeters, up the field. So this is going to give us an electrical field, or an electrical potential of 2 joules per coulomb, or 2 volts. And this is going to be the units of voltage. So volts is the unit of voltage. So now let's see how we can use that potential that we found in the previous slides in order to find the potential energy. So for gravitational potential, you're going to multiply that by the mass, and that's going to give you that gravitational potential energy. For electric potential, it's going to be something very similar. You're going to take that electric potential, the voltage, multiply that by the charge, and that's going to give you the electric potential energy or electrical energy. Let's go ahead and do some examples with this. So using the same numbers that we have, let's find the gravitational potential energy of a 100 kilogram object if its gravitational potential is 19.6 joules per kilogram. And you might remember that that's the gravitational potential that we found earlier, 2 meters above the ground. So that gravitational potential energy is equal to the gravitational potential times the mass. Plug some numbers in, so that 19.6 joules per kilogram potential multiplied by that mass of 100 kilograms. Kilograms are going to cancel, and this is going to leave us with an answer in joules of 1,960 joules. We can do something very similar when it comes to electric potential. So if we wanted to find the electric potential for a 100 microcoulomb particle in an electric potential of 2 volts, we can do that. What we're going to do is to find that electric energy, we're going to have that equal to the voltage times the charge. So 2 volts times 100 microcoulombs is going to give us an answer of 2 times 10 to the negative 4 joules. So now you should be able to calculate the gravitational potential energy through both that force times the height and by that gravitational potential times the mass. Similarly, hopefully now you are able to calculate the electric force based off the strength of an electric field and its charge, calculate the electric potential energy by multiplying that electric force times the distance that you've moved in that field, and also calculate the electric potential, which is the voltage based off of the electric field and the height that you are in it, and then finally that electric potential energy based off of the voltage and the charge of a particular object. Thank you very much, and have yourself the most wonderful of days.